everybody. Welcome back to Mathematical Statistics. At the end of the last video, we were talking about unbiased estimators and liking estimators that have small variance because they are more predictable, because the estimators are random variables. And even if they are on average correct, they could be swinging wildly around that point you're trying to estimate. So continuing here, I want to introduce a new distribution, which I'm sure is not new to most of you, but we haven't talked about it in here yet. And that is the uniform distribution. Now there's a uniform distribution on both discrete sets and continuous sets. And here I want to talk about it on a continuous set or interval. So I'm going to say on the interval from 0 up to the unknown theta. So there's the parameter for this distribution. And I could have used square brackets there, both on the left side, right side, or both, because we're talking about a PDF where area under the curve represents probability, and there's no area on those particular straight lines under the curve. So it really doesn't matter. But let's draw this. So even if you didn't know what this distribution is, I did just say it is the continuous version of equally likely. So we're talking about values that go from 0 to some theta. And if all the values in between are equally likely, then if you look at like some interval over here and you slide it down here, but keep the same width and also stay within the two bounds, we want to get the same probabilities. And if you keep sliding them around, you want to get the same probability no matter where you put that subinterval. So this forces the PDF to be a flat line. Nice and uniform. And because this is now like a rectangle, the area under this PDF needs to be 1, which means the height of the rectangle needs to be 1 over theta. So we can write the PDF. You could just call it f of x, but I'm starting to move into this notation semicolon theta, where we really show that dependence on a parameter. And this is just going to be the constant height, 1 over theta, and then an indicator that says that x is between 0 and theta. And again, you might see this, and you might use this with some square brackets on that indicator interval. It doesn't matter. But let's, for my first sort of question here, let's find an unbiased estimator for theta. So we're just going to come up with one out of the blue. And if you think of like sampling values and you don't know theta, so you don't know the right endpoint of this interval, when you sample values, you'll start getting values all over the place. And if that's maybe my n values, I think maybe, I don't know if you agree with me, my best guess for theta might be to look at the maximum value in my sample. But I also think that could be a little off, because unless we have a huge sample as n goes to infinity, I don't think we're going to actually make it all the way up to theta. So I think we should look at the maximum for trying to estimate this right endpoint, but I don't believe it will be unbiased. But let's start there. So I'm going to try to look at the maximum. So the first thing I want to do is look at the expected value of this maximum and see if we get theta. And I suspect we won't, but when we see the answer, we may be able to adjust what we started with so that we do get theta. So how do we get the expected value for this maximum? We need to find the PDF for the maximum, and you may have remembered or memorized that formula, or you might, like me, start with the CDF, which does require the CDF for the individual x's. So if this f of x, this capital F, is the CDF for any one of them, so not the max or the min, but just one of the values in a sample, oh yeah, we need a sample. So I'm going to suppose that x1 through xn are IID from this uniform distribution on 0 to theta. So based on that sample, I want to come up with an unbiased estimator for theta. And I think it kind of makes sense maybe to look at the largest value in the sample. for estimating the right endpoint of that interval. So this is continuing. This is the CDF or the PDF up here. And if you put down any X, you want the total area up to X. So I don't need to integrate to tell you that the area of that little rectangle is X times 1 over theta, or X over theta, and that the X's live between 0 and theta. And I don't know if you recall, I had a conversation towards the beginning of the semester where I don't really like to use indicators with CDFs, but you certainly could. So I just want to keep in mind at least that X is between 0 and theta. And this is not a and 0 otherwise statement. This would actually be 1 if X is greater than or equal to theta, and 0 if X is less than 0. And it kind of matches up at theta, so I'll put an equal sign there as well. So that's the CDF for any one of the X's. So we're ready to go for the CDF for the maximum. I need to know the distribution of the maximum before I can find its expected value. So that's what I'm going for. The CDF for the maximum is the probability that the maximum, so that's what that n in parentheses is less than or equal to X. And you may have memorized a formula, but I usually try to think about what this means in terms of the individual X's. And there's only one way for a sample to fall so that the maximum is below X. And they can be in various positions, but the maximum being less than or equal to X happens if and only if each and every one of those X's is less than or equal to X. So this is the probability that X1 is less than or equal to X, and X2, same thing there, out through Xn less than or equal to X. And then we say they're independent, so I get to multiply these, and they're identically distributed, so I really just get one of those to the nth power. So we are down to, because they're IID, the probability that X1 is less than or equal to X to the nth power. But we have that probability up here. This is X over theta to the nth power. And yes, you can write that all piecewise, but I'm not going to bother. I'm just sort of looking at the CDF where it's interesting. And this is the CDF for the maximum and the minimum, and any order statistic like the second smallest or second largest lives on the same space as the original X's. So this means that X is between 0 and theta. And again, we could put, equals under either of those inequalities or both of them. But we're ready to get the PDF, the probability density function for the maximum. And to get that, I'm going to take the derivative of the CDF. Now, this is the derivative with respect to X of, let me rewrite this so it's maybe easier, maybe not, I don't know. This is, actually, I'll leave it. So X over theta to the n, and if we take the derivative, we'll get n times X over theta to the n minus 1, and then a little chain rule action, the derivative with respect to X of what's inside the parentheses, so that's 1 over theta. But now I do think I want to organize this so that the X is separate from everything else. So we could write this as n over theta to the n times X to the n minus 1. And this is for X between 0 and theta. And the PDF is 0 otherwise. The CDF is 0 sometimes and 1 sometimes outside of the region, but the PDF is 0 otherwise. So if we wanted to write this down sort of cleanly, this PDF for the maximum is n over theta to the n, X to the n minus 1, and then an indicator that says that X is between 0 and theta. X is just an argument here. So when I'm working with mins and maxes, I don't put like a lowercase xn with parentheses in there. That's just cumbersome to carry around. So it's just an argument, and you can put whatever you want in there. And I chose to put an X in there. But now that we know the PDF for the maximum, we can find the expected value for the maximum. This is the integral in general minus infinity to infinity of x times the PDF for the maximum. And then that PDF is 0 in a whole lot of places. So the indicator is going to cut us off from 0 to theta, and we'll get x times n over theta to the n, x to the n minus 1 dx. And I will pull those constants out. And I've got 0 to theta. I'll combine the x's, x to the n dx. And if you integrate that, you get x to the n plus 1 over n plus 1, evaluated from 0 to theta. And when you plug in theta, you get n plus 1 thetas in the numerator, but you have n in the denominator. And you end up with, of course, when you plug in 0, you get 0. But you end up with n over n plus 1 theta. So the maximum is not an unbiased estimator of theta. We want this to be theta if we want an unbiased estimator. So before proceeding, let me just point out that the coefficient kind of makes sense in that it is less than 1. And if you have an interval and you don't know the right endpoint, but you collect some data, your best guess maybe for the right endpoint is the maximum, but we already talked about how that's not really going to kind of snug up against that right endpoint. We do expect that to be smaller than theta, and that is what we're seeing here. So how to get an unbiased estimator? I started with just what I would call a common sense estimator. Please don't feel bad if it's not common sense to you. It just feels right to me. You know, we're trying to estimate an unknown right endpoint of an interval, and we've got the data. So I would look at the largest piece of data. And we didn't get theta, we got this. But if I flip this over and put it up in here, then we'll get the right thing, because the expected value of n plus 1 over n times the maximum, that constant can come out. And then we just did that expectation, and we got n over n plus 1 theta. So I've put something in front that's going to cancel everything out and give us theta. So here is an unbiased estimator. And there's many more, but an unbiased estimator of theta is, since I'm going to have another one, I'm going to call it theta 1 hat. And it's going to be this thing whose expected value is theta. So n plus 1 over n times the maximum. So we're done with my proposed question 1, which was to find an unbiased estimator for theta. And I don't know if that makes sense to you, but I thought the right endpoint of the data, the maximum value, would be a good thing to look at. Let's look for another unbiased estimator. And I don't know why you would think of this one, so let me give you a hint. Let's find another unbiased estimator. So I'm still dealing with this uniform 0 theta for theta based on, I'm going to be doing this based on quite a bit at the beginning of this semester. I'm going to give you a statistic to consider and start with, and you should look at its expectation and see if you can't adjust it if it's not unbiased. So I want to do it based on the sample mean x bar. And we do know that the expected value of the sample mean is the same as the expected value of any one of them. from the random sample x1 through xn. So to find that expectation, you could do an integral, but I claim you don't have to. The mean is a balancing point for the distribution. If you think of it as a center of mass thing that you might have learned about in calculus. So the mean is not for a generic PDF. It's not going to be necessarily in the center of the interval. If there's more area up here and less here, the mean is going to be pulled down here because more values come out close to zero than close to theta. But for something that is a flat line like this, the center of mass here is right in the center. And in fact, if you go to your table of distributions, you'll see that the mean for any one of them is theta over 2. I think it was written differently. I'm not sure which version of the table you have, but I think it's something like alpha to alpha plus beta. And in our case, alpha would be 0 and beta would be theta. So finding an unbiased estimator for theta based on x bar, if someone asked me to do that, the first thing I would do would be to look at the expected value of x bar. And then it's not quite theta, right? So we're not there yet, but we are really close. So let's adjust it and say that another unbiased estimator for theta is, I'm going to call this theta 2 hat, and I'm going to take 2 times x bar, because if I put a 2 right in there and it just followed all the way through, it would cancel with the 2 in the denominator over here, and we would just get theta. So here is a second unbiased estimator. Which one is better? We are still in the process of defining good, better, and best, but so far we know that if we're choosing between 2 unbiased estimators, we would like to choose the one that is sort of more tightly concentrated around that mean that it's estimating. So smaller variance. So let's compare the variance for these estimators. Okay, so the variance for theta 1 hat, now that was this thing in the box up here. So this is the variance of n plus 1 over n times the maximum. And I've got a constant in front of my random variable. It would pull out squared, so I get n plus 1 over n all squared times the variance for the maximum. And we know that we can define this variance for the maximum as the expected value of this maximum squared minus the expected value of this maximum all squared. We learned that in the last class. Now we already computed this expected value of the maximum alone, and that came to this right here, n over n plus 1 theta. So let me write that in. This is n plus 1 over n squared, expected value of the maximum squared minus n over n plus 1 times theta. And all of that gets squared. So what remains for us to do is this expectation. And we already did the hard work. The expected value of the maximum squared is going to be the integral from minus infinity to infinity of x squared times the PDF for the maximum. And this PDF lives on 0 to theta, so it is going to get cut off. This is going to be the integral from 0 to theta of x squared times n over theta to the n x to the n minus 1 dx. So I'll pull out the n and the theta squared and integrate 0 to theta x to the n plus 1 dx. This should be this superscript down here should be an n. Okay, so when you integrate that, you're going to get x to the n plus 2 over n plus 2, and you're going to plug in theta. So you'll get theta to the n plus 2 over n plus 2. So you'll get several thetas canceling, and you're left with n over n plus 2 theta squared. So now I'm going to go back up here and plug this in. And so recapping, the variance of theta 1 hat is n plus 1 over n squared times this thing we just computed minus n over n plus 1 theta all squared, which is n over n plus 1 squared, theta squared. So let me pull out that theta squared. Here I've got n plus 1 squared over n squared, n over n plus 2. When I square this, I get n squared over n plus 1 squared, and I can pull out the theta squared. So as a something to know for this class, I don't care if you simplify your answers unless I specifically say simplify. But because I do want us to go on and find the variance for theta 2 hat and compare, I think it's going to be a good idea to try to simplify this. So I've got n plus 1 squared over n squared and a common denominator in here. And this is, just have to finish, I guess. I wish I'd worked this out. And then I get this cancels with this and this with this. And I get this with one of these. And I get all of this with all of this. So we're doing good here. We have a lot of cancellation. I can write this as what's left in the numerator, just 1. All right, just 1. 1 over n plus 2. The n coming from here and the n plus 2 over here, theta squared. Okay, so let's look at the variance of our other unbiased estimator, theta 2 hat. And this one was 2 times x bar. Now that constant comes out, but it comes out squared, so we get 4 times the variance for x bar. And last time we showed that the variance for x bar is just the variance for any one of them over n. And unless I specifically asked you to work that out from scratch, you can go to the table. The variance is a kind of strange thing, I think, for the uniform with length beta for the interval. You'll see in the table, the variance is beta squared over 12. And if you need practice, you can work that one out. So in our case, theta squared over 12. And then we've got the n here. So altogether, this is 1 over 3n theta squared. So let's compare these two variances. They both depend on theta squared, which is unknown because we're trying to come up with an estimator for theta, so we don't know theta squared. But fortunately, they're both just a constant times theta squared. So if one of the constants is smaller than the other one, we'll know which variance is smaller. Back up here, this is 1 over n squared plus 2n. And here I have a 3n. So n is a positive integer. It could be 1, 2, 3, 4 on up. If n is 1, then both of the circled variances are equal. But if n gets larger, this n squared grows faster than like 2n plus n, which is really what's going on down here. So I've got that the variance of theta 1 hat, which is this guy, The denominator is larger than this denominator, so overall it is smaller or less than or equal to the variance for this guy. So from these two unbiased estimators, given all we know so far about estimators, theta 1 hat is better. Unbiased with smaller variance. Unless that's not how you define better. That's why I put it in quotes. Better is kind of subjective. Okay, so at the very end of the last lecture, I was talking about how you might want a little bias in your estimator, meaning it's not unbiased, if the variance is very small, which means that your estimator is very predictable. So forget this uniform. We're done with this example. Suppose I am trying to estimate theta, and suppose I have a statistic like X bar or something, and that has its own distribution, and it's nice and centered by weight, right? Again, the number that cuts the PDF into 50% area is something known as a median. So the mean is not in the middle in that sense. But if this is symmetric, it would be. That's supposed to be symmetric. So your theta hat PDF might look like this and be on average correct. But I don't know what numbers I have on here, but maybe this is like 1 million here. Maybe it's got a lot of spread. So even though on average you'll get the right value, if you only get to grab one sample of those students on campus who you're measuring, you would hope to not be so wildly varying. And an option might be, well, the best thing would be for us to have an estimator that is also unbiased, but with smaller variance. It's supposed to look symmetric as well. And, but what I'm trying to get at is, would you accept a trade-off? Something that its expected value is a little bit over here, but it's highly predictable with very small variance. So when you get into statistics, everyone, myself included, gets way into the unbiased thing, but that's not the be-all, end-all for estimation. And maybe you want a smaller variance, and you might do a little trade-off for bias. So recall that for a random variable x, the variance for x is the expected value of x minus its mean squared. And this mean, mu, is the expected value for x. Now that we're talking about estimation, our random variables are the estimators, the theta hats. So the variance for theta hat is the expected value of theta hat minus its mean. So the expected value of theta hat squared. Like up in here, I could have written the expected value of x, except we have notation for that. But if our theta hat is an unbiased estimator for theta, this is just going to be theta. So if we have an unbiased estimator here, this is going to be the expected value of theta hat minus theta squared. This is the estimator, and this is the thing we're estimating. And so this thing is known as the mean squared error. You're taking how far off you are and squaring it and averaging it. And sometimes this is the variance. But if you have a biased estimator, this mean squared error, which is actually defined as this, is not quite the variance. So next up, I'd like to see the relationship between mean squared error and variance. So let's take a look. Before doing this, I just want to give you one more definition, and that is the bias of an estimator, theta hat of theta. I'm going to write like a capital B. I don't know. For some reason, I switched to parentheses. Square brackets are fine. But this is defined. Let me get a colon in there. This is defined to be the expected value of your estimator minus the thing you're trying to estimate. So theta hat is a random variable, but when you take the expected value, you do get a real number, and this is a real number. So this whole thing is just a number. If it's positive, you have some kind of positive bias saying on average, your estimator is coming out above the true theta. And a negative bias means on average, your estimator is coming out below the true theta. But this is how we define bias. And if you ever get confused about which goes where, it probably won't matter because we almost always use bias when it's squared, as we're about to see. So let's look at the mean squared error for theta hat. Theta hat is an estimator for theta. So the mean squared error is the mean or expected value of the square of the error, the difference between theta hat and theta. And as we know, if theta hat is unbiased for theta, then this is the mean for this. And this is simply the variance for theta hat. But let's not assume that that's the case. Let's write this. I'm going to write this as theta hat. And I kind of want to relate it, really read that. I kind of want to relate it to variance. So how would you get the variance for theta hat? You would subtract the mean for theta hat. But of course, that's not equal to what's over here. So I'm going to add that back and then subtract the theta and square it. So I've just written the same thing, but I've put this minus and plus term in the middle, which will cancel each other out to give us this back. This over here is the bias. So let me write this like that. This is the expected value of theta hat minus the expected value of theta hat plus the bias of theta hat all squared. And I am going to square this now, but I'm going to keep this grouped. So it's really like in A plus B that I'm squaring. This is the expected value. So I can write out a really long thing here. And then in the next line, run the expectation across. I'm going to just run the expectation across at the same time here. So let me know if this doesn't make sense. I will get the expected value of theta hat minus the expected value of theta hat, all of that squared. The next term, I'm going to get 2, I'm just squaring something, the expected value of this times this. That bias that I just circled is non-random. Up here, you can see this is a number and this is a number because we've averaged out the randomness from theta hat. So I can pull out the bias from that expectation because it's constant, and I'm left with the expected value of theta hat minus the expected value of, what am I trying to say? Theta hat. Oops. Plus the bias squared, and the expectation of the bias squared is just the bias squared. So again, maybe I should have written some extra lines, but I'm taking this plus this all squared. I'm squaring it out, but I'm leaving these two grouped together, and I'm running the expectation through. So after running the expectation through, you'll have like a 2 bias inside that can then be pulled outside. Okay, let's look at real quick this middle term, actually just this part. If I run the expectation across this, I get the expected value of theta hat minus the expected value of theta hat. So the expected value of theta hat is a constant, it's not random. So if I take the expected value of that, I just get the expected value of theta hat. So what I'm trying to say is this is the expected value of theta hat minus the expected value of theta hat. Now this equals 0. So out of the 3 terms I have in the line above, after squaring and running the expectation through, the center term actually disappears. And I'm left with this one, which is the definition of the variance. Here is a random variable. Here is its mean or expected value. You square that difference and take the expectation. So the first term is the variance for theta hat. The second term is 0. Let me just write that so you don't have to wonder what happened. And then the final term is the bias squared, or bias, all squared. But this is the MSE. So here it is, the formula in the box. The mean squared error of an estimator theta hat for theta is the variance for the estimator plus the bias for the estimator squared. And if you have an unbiased estimator, this bias will be 0. So we are again seeing that if you have an unbiased estimator, mean squared error is identical to variance. Pretty cool, right? Let's look at another example of finding an unbiased estimator. And this one is going to use a whole bunch of skills we have and things we already learned using moment generating functions. So I think it's a pretty good example. Let's take a random sample, x1, x2, out through xn, IID, from the exponential distribution with rate lambda. So part 1 of this example is going to be to find an unbiased estimator, not for lambda, we're getting there, for a function of lambda. So tau of lambda, where this function is defined to be 1 over lambda. You might recognize 1 over lambda to be the mean of this distribution. And we said last time that the sample mean is always an unbiased estimator of the mean of the distribution. So I think we should take our estimator for this function to be x bar, because if you take the expected value of this, it turns into this expected value and it turns into this. And so we are done with finding at least one unbiased estimator. And we will get to lambda, but this is obviously much easier because it's the mean of the distribution, and we know that sample means are pretty good and definitely unbiased estimators for true means. As a second point here, let's find another unbiased estimator for this tau of lambda equals 1 over lambda. And the first one we looked at was kind of, yeah, we're always going to try the sample mean, especially if the thing we're trying to estimate is the mean of the distribution. As this course progresses, you're going to have algorithms, you're going to have technique steps for finding these things. But right now, if it's not a common sense kind of obvious thing, I hate to say obvious, but I'm mostly going to tell you this. I'm going to say based on the minimum value in the sample. Why the heck would I look at the minimum value of the sample? to try to estimate 1 over lambda, especially since we've already estimated 1 over lambda. The only reason I'm looking at it here is because it's easy, because we did show that the minimum of NIID exponentials with rate lambda is again exponential with rate n lambda. That was number 3 in our 4 important tools for mathematical statistics. Let's recall. So the expected value of the minimum is the expected value for the exponential is 1 over that rate parameter. But I want to see 1 over lambda, not 1 over n lambda. So like a tau of lambda hat 2, like a second estimator, would be n times the minimum, because that is what I need to put in front so that it will cancel to 1 over lambda. And we've done it. We have a second unbiased estimator. Let's compare the variances. The variance for the original tau lambda hat, which you might call tau lambda hat 1, we do have a tau lambda hat 2, is, so that estimator was just x bar. So this is going to be pretty quick because we know the variance for x bar is the variance for one of them over n. And if you look up the variance for the exponential in your table, or if you know it, it's 1 over lambda squared over n. So we get 1 over n lambda squared. The variance for the second unbiased estimator, again, why would you look at the minimum? Sometimes you look at the only thing you can, the only thing you know the distribution for. So if we're not estimating the mean of a distribution, we're not going to have that go-to estimator, the sample mean, and it's going to be trickier. So sometimes we're just going to have to work with the things that we can work with, that we can find the distribution of. But this is the variance of n times the minimum. I'm going to pull out that constant, but it comes out squared from a variance. And recall that this thing inside has the exponential distribution with rate n lambda. And so just like the variance of the exponential with rate lambda is 1 over lambda squared, the variance for the exponential with rate n lambda is 1 over n lambda quantity squared. So I get n squared just sitting out here, 1 over n lambda squared. And I get 1 over lambda squared, 1 over lambda squared. Yeah, so the variance for the first one looks better because it's smaller. If n is 1, they're actually equal. But the first one, as n gets larger, the variance gets smaller. And that is another thing you're going to want out of your estimators. You're going to want them to get better with more information. Bigger samples, smaller variance. It doesn't have to be the case. This one will not change at all, no matter what your sample size is. So not only is this variance larger than this variance for n greater than 1, but this one's not even moving at all. So for that reason, I would say our second estimator for 1 over lambda is pretty bad. So right now we can say the first estimator, the one that is uh, tau lambda hat equals x bar, is better because when comparing two unbiased estimators, you definitely want the one with smallest variance. Okay, let's make this more interesting. So for part 4, now I want to go for lambda. I want to find an unbiased estimator for for lambda. This is no longer the mean of the distribution. So it's not, the sample mean is maybe not your go-to thing. But we do know that the expected value of x bar the sample mean, is the expected value of one of them. And that is 1 over lambda because that's the mean of the exponential distribution. So I'm going to try, motivated by this, I'm going to look at the expected value of 1 over x bar. Now, this is absolutely not equal to 1 over the expected value of x bar, but maybe it will get the lambda in the right position so that we can adjust it. These are not the same for the same reason that 1 over an integral of x and fx dx is not equal to the integral of 1 over x, fx dx. It's just expectations just don't work like that. However, I do want to try it, and maybe we can work with it and adjust it. So I'll write that again. We're going to try the expected value of 1 over x bar. I am going to write that denominator as 1 over n, sum of the x's, which means that I will have an n on top ultimately, and the sum of the xi. And I don't want to be dealing with an expectation from an n-dimensional PDF because this is like a g of x1, x2 out through xn. Fortunately, we can look at the distribution of this and think of this as a one-dimensional thing. So this is the expected value of n over w, where w is the sum of the xi, and that sum goes from 1 to n. And we already know its distribution, but if you didn't remember it at this point, then it's a quote-unquote big fat sum, and I would use moment generating functions to find the distribution. I'm going to skip that. We have done it. I'm not saying it's supposed to just come back to you in your memory. Eventually it will because we use this so much in this course, this particular fact. But when you add up NIID exponentials, you get a gamma. The first parameter is the number you added together, so n. And the second parameter matches that of the exponential, at least the way we have defined and parameterized PDFs in this class. Still, how are we going to get I know the expected value of the gamma, but I don't know the expected value of 1 over the gamma. So let's see what we can do. The expected value of 1 over x bar is this. I'm going to pull the n out. This is the expected value of 1 over w, where w has that gamma PDF. I'm going to write out what this is. I'm going to spare the generic thing. I'm going to go straight to 0 to infinity, 1 over w times that gamma PDF, which is 1 over the gamma function at n, lambda to the n. I'm using w as my variable here, w to the n minus 1, e to the minus lambda, w dw. This looks like a hairy integral. Let's combine the w's. I've got a w part here and here. How are we going to integrate this? If you just look at, ignoring constants, like this is a constant, this is a constant, this is a constant. If you just ignore those and sort of look at just what kind of function this is, just this part, that appears to be a gamma PDF if you had the right constants in the front. So this is like a gamma PDF. So the gamma PDF had x to the alpha minus 1, e to the minus beta x, and then some stuff in the front. So it appears that alpha here is n minus 1 because this exponent is that minus another one. And then the beta exponent appears to be lambda. So let's make the stuff in front correct. Let me start with that. I would like this to be 1 over gamma of n minus 1, lambda to the n minus 1, w to the n minus 2, e to the minus lambda, w dw. That is this PDF. And that integrates to 1, but that's not equal to the line above. So let me throw in the n that's sitting here, this 1 over gamma of n that I basically pulled out. I need to pull out a single lambda to leave me with n minus 1 in there. So to get from lambda to the n to lambda to the n minus 1. And then in order to put this in the denominator, I'm going to need to multiply by that up in the numerator. And this whole integral is 1. So we've got n lambda gamma n minus 1 over gamma of n. And there's two ways you might simplify this. We have shown that the gamma distribution evaluated at integers, gamma of n is n minus 1 factorial. So I'm going to write this as n minus 2 factorial over n minus 1 factorial. But another way you can do it is use the fact that gamma of alpha is, if alpha is greater than 1, is alpha minus 1, gamma alpha minus 1. And so you might write this denominator as n minus 1, gamma n minus 1, and then cancel those gammas. I'll keep going with this one. I've got n minus 1, n minus 2 all the way down in the numerator, in the denominator, and n minus 2 all the way down in the denominator. So when I cancel terms in here, I do just get n minus 1 in the denominator. So overall, we get n over n minus 1 lambda. I would definitely pull the lambda out and not like write it up here because we are looking for an unbiased estimator of lambda. So we'd really like to see it as some constant that hopefully we can adjust times lambda. So all of this was, in case you forgot, the expected value of 1 over x bar. We were in the third question or the fourth question in this example where we were trying to find an unbiased estimator for lambda itself. We knew that x bar was unbiased for the mean, 1 over lambda, so we tried 1 over x bar. And we didn't get over lambda, but we got close. So the unbiased estimator for lambda is n minus 1 over n times 1 over x bar. In other words, I'm taking this and flipping it over there so that if you run the expectation across, you would cancel things out and just get lambda. And that's a fine answer. Or if you think of this denominator here as 1 over n times the sum of the x's, you can get some cancellation. This is n minus 1 over the sum as I goes from 1 to n of the xi. So kind of close to 1 over x bar, but not exactly the same. Okay, so we have an unbiased estimator for lambda, and we only have one of those, so I'm not calling it lambda hat 1 and lambda hat 2. So the next part 5, I want to find the variance of this unbiased estimator from part 4. So the variance for lambda hat is going to equal the variance for n minus 1 over the sum from 1 to n of the xi. I'm going to pull out the n minus 1, but it comes out squared. And this is going to be the variance for 1 over w, where w is defined to be that sum. Just remind you up here. And we know, starting with exponentials, that this has a gamma distribution with parameters n and lambda. So I can compute this variance several ways, but one way would be to write this as the expected value of 1 over w squared minus the expected value of 1 over w all squared. And we did just work this one out. The expected value of 1 over w, I have to be careful because like this answer here is not 1 over w expectation, it's this. So it has an extra n in it. And so this is 1 over n minus 1 lambda, and that whole thing gets squared. The only thing we need is this expectation. So I'm going to do it in the same way, and I'm going to go a little faster. That w has the gamma distribution, so I can compute this as the integral 0 to infinity 1 over w squared times that gamma PDF. You can use x's if you want. It's an integral and you're going to plug stuff in. But I have this W piece and this W piece, so I'm going to pull them together. This should be a dW. And I'm going to ignore the constants and just look at this and say that kind of looks like a gamma PDF again. This is like a gamma n minus 2 lambda PDF because I'm looking for x to the alpha minus 1 e to the minus beta x. So I have like x to the n minus 3, which is n minus 2 minus 1, etc. I do need my alpha to be greater than 0. I need that exponent up there to make sense. So we do need, oops, we do need the sample size to be greater than or equal to 3, or this doesn't make sense. You could continue the problem, but you could say the variance of my estimator is infinite if I only have such a small sample. So assuming that n is greater than or equal to 3, I'm going to make this look like the correct gamma PDF. I have 1 over gamma of n. And in here, I want 1 over gamma of n minus 2. So I want a gamma of n minus 2 out here. I want lambda to the n minus 2. You'll recall that the PDF it had gamma stuff, but it had beta to the alpha, x to the alpha minus 1, e to the minus beta x, and a constant. So I do want the beta to the power to be just one more power than the x part. In this case, my beta is lambda, so I have an n minus 2. So it's like one more than the n minus 3. And then this isn't the line above. I have lambda to the n minus 2 and lambda to the n here. So I'm going to need a lambda squared out here. And now the lines are equal. And this is the integral from 0 to infinity of this gamma PDF. So I know this is 1. And this is going to be n minus 3 factorial over n minus 1 factorial lambda squared. And we'll get a bunch of cancellation there. This is 1 over n minus 1, n minus 2 lambda squared. So we're not done with the problem. That was just this expectation. Okay, let's pull it all together. I have a lambda squared over here and a lambda squared coming out of this expectation. So I'm going to go ahead and pull the lambda squared all the way out. I'm going to start with this n minus 1 squared. What is this called? The variance of lambda hat. This is n minus 1 squared something times lambda squared. And that something is what we just found. So 1 over n minus 1, n minus 2, minus 1 over n minus 1 squared. Okay, you could stop there if I was just asking for the variance, but usually I'm going to ask this in the context where you have to compare it with another variance. So let's just clean this one up. We'll get some cancellation. The top, everything goes away. It's 1. So we get 1 over n minus 2 lambda squared as the variance of our unbiased estimator for lambda. I am almost out of time. Let me just hint at what was coming next. We were still in this example. To estimate lambda, we took 1 over x bar, but that wasn't quite right, and we adjusted it. But what if we use the estimator lambda 2 hat to be 1 over x bar? So remember, this is biased. Its expectation is not lambda. Here's where we should start talking about mean squared error. So what is the mean squared error for lambda 2 hat? We'll do that next time. But by the way, the mean squared error for lambda hat, which now I kind of want to call lambda 1 hat, but this is our lambda hat, is because it's unbiased, is the variance. And we've got it right there. So don't put that past me on an exam to have you show something unbiased, find the variance, and then in part C, find the MSE, where you can say, it's unbiased. I already did this. This is the variance. You don't have to do it from scratch. But this one we will have to do sort of from scratch, and I'll start with that next time. And then we're going to start talking about large sample properties of these estimators. So we've seen things today like, I don't know exactly what they were, but like things like n over n plus 1 as expectations, and they were biased. But as n gets large, this goes to 1. So we could talk about it being quote unquote asymptotically unbiased. And next time, we're going to talk about lots of types of convergence for sequences of random variables. Next time on mathematical statistics.